Greetings everyone, welcome to A&E Learning Hub. I'm going to go through and explain the solutions for question 5 from the 2018 Csec Electrical and Electronic past paper. So let's begin. Part 1 of A. It says, sketch the logic symbol for a 2-input AND gate. So here's the symbol for the 2-input AND gate. A and B are both the input, and Y is the output. Now, the mathematical operation for the AND gate is multiplication. So it means that A and B would be multiplying in order to get Y. All right, so that's it for part 1 of A. For part 2, it says, with the aid of a diagram, describe how single pole, single throw switches may be used to represent the operation of a 2-input AND gate. So here we have a diagram with 2 switches, A and B. They're connected in series with each other. If switch A is to be closed while switch B remains open, the lamp will not turn on. If both switches are to be closed, then the lamp will turn on, and that represents how the AND gate would operate. Because if we're multiplying both A and B in terms of input, so if we were to have 0 going in, that's at A, so that means that A would be open. So A would be open, and have 1, which is a high, would be going in at B. So that means at the switch here at B, the switch would be closed. So we'd multiply 0 and 1, and we'll get 0 on the output. So based on the circuit diagram here, so you see that the lamp will not turn on. Why? Because A is open. If you were to have a high input now, so moving from 0 to 1, so it means that A here will become closed. So 1 multiplied by 1 will give you 1, which is a high output. So it means that the light will now turn on because switch A and switch B is closed. All right. So by connecting 2 single pole, single throw switches in series, right, that will represent the operation of a 2-input AND gate. So that's it for part 2. For part 3 of A, it says, state the mathematical expression for the output Y of this logic gate. So as I said before, the mathematical operation of the AND gate is multiplication. And in order for you to get the output Y, you have to multiply A and B to represent that where logic gate is concerned. So Y is equal to A dot B. The bracket is not really necessary, so you don't have to worry about the bracket. All right, so that's it for part 3. All right, so let's move on to part B now. It's part 1 of B. It says, sketch the logic symbol for a 2-input OR gate. So this is a symbol for a 2-input OR gate. And for the OR gate, the mathematical operation for the OR gate is addition. So it means that in order to get the output Y, you will have to add A and B together. All right, so that's it for part 1 of B. For part 2, it says, draw the truth table for the 2-input OR gate sketched in part 1 of B. So here we have the truth table for the 2-input OR gate. Now, I know that some of you, for exam purpose, you will try to remember the truth table. All right, so you don't have to try to remember the truth table. So this is what you have to do. So once you have the input and the output side set up, so for the input, you will have to enter the number of possible combinations of 0 and 1, right? So those combinations cannot be repeated at all. So looking at the input here, so you have 0, 0, 0, 1, 1, 0, 1, 1. So these are the only possible combinations of 0 and 1 that can be entered in the input part of the truth table. All right, so for the output now, then you'll have to apply the operation of the OR gate. So 0 plus 0 gives us 0. 0 plus 1, 1. 1 plus 0, 1. 1 plus 1, 1. All right. So that's how you can develop the truth table. All right. So that's it for part 2 of B. So for part 3, it says, with the aid of a diagram, describe how single-pole, single-throw switches may be used to represent the operation of a two-input OR gate. So here we have the circuit here. As you can see, we have the two switches A and B. They're connected in parallel, and that's how they're connected to represent the operation of a OR gate. Now, we're going to verify that this circuit is correct by using both the circuit and the truth table. Now, for the first row, so for A, we have 0, which is low. So on the circuit where the switch is, so low would mean that the switch is open. For B, it's also low. So it means that the switch B here would be open. So it means that no current will be flowing through the circuit and the lamp would be off. Let's go to the second row. So at A, a second row, we have a low signal, which is 0, which means that A will be open. And at B, we have an I signal, which means that the switch at B here will be closed. Now, the fact that the switch here is closed, we have a path for current to flow through the circuit. So it means that the lamp will now turn on. So it means that you'll now get an output, which is what we have here. All right. So for the third row, so A is I. So it means that for the switch at A should be closed, and B is low, so it means that B should remain open. So again, there is a complete path for current to flow, so it means that the lamp will turn on, so you'll have a I output. For the fourth row, both A and B are high, so it means that both switches will be closed. So the fact that both switches are closed, what that means is that there's a path for current to flow throughout the circuit. So it means that the lamp here will turn on. So you'll get a I output as indicated in the truth table here. All right, so that's it for part 3. All right, so let's move on to part 4 now. So it says, state the mathematical expression for the output Y of the logic gate. Now, remember I stated earlier that the mathematical operation of the OR gate is addition. So it means that in order to get the output Y, you'll have to add A and B together to get Y. So hence, Y is equal to A plus B. All right, so again, don't worry about the bracket. The bracket is not important. All right, so that's it for part B. All right, let's move on to part C now. So it says, given that the output Y of a logic circuit is high when the two inputs A and B are both I, and also when the two inputs B and C are both I. Part 1 of C, it says draw the truth table for this combinational logic circuit. So here I have the truth table. As I said before, where the input side of the truth table is concerned, all you have to do is to enter the number of possible inputs where ones and zero is concerned. So for the first row, we have 0, 0, 0. That's for A, B, and C input. For the second row for A, we have 0. For B, 0. For C, 1. For the third row, have for A, 0. For B, 1. For C, 0. For the fourth row, for A, 0. For B, 1. And for C, 1. For the fifth row, for A, 1. For B, 0. For C, 0. For the sixth row, for A, 1. B, 0. C, 1. For the seventh row, A, 1. B, 1. C, 0. For the eighth row, A, 1. B, 1. C, 1. So all you have to do is to enter the number of possible combination where ones and zero is concerned. And remember, any combination that you would have entered for the input side, it cannot be repeated. So if you look at what I have here, the combination for both A, B, and C, they haven't been repeated. All right. Now, based on the criteria that was given, all right, so it says the output Y of the logic circuit is high when two inputs A and B are both high. So we need to look for when A and B are high, then we'll have an I output. All right, so here we have A, I, B, I. So it means that we're going to have an output of I. All right, good. So the second criteria is that Y will also, which is the output, will also be I when two inputs B and C are both I as well. So for B, here we have an I, and for C, we also have an I here. So it means that we're going to have an I output. So based on the criteria, it means that the remainder would be 0, except for the last one here, because based on the criteria, it tells you that when A and B are both I, the output will be I, and also B, C, I, so the output will be I. So if you have all of them, A to B, A to C, I, then it means that the output will also be I. All right, so now that the truth table is completed, let's move on to part 2. So it says design a logic circuit that meets the criteria for this combinational logic circuit. All right, so here I have the circuit for the criteria that was given in part C. Now, what I'm going to do is to verify that this circuit is the correct circuit. All right, so I'm going to use multisim, which is an electronic simulator. All right, so let me pull that up. All right, so here we go. So let's go back to the truth table. So here we have our inputs A, B, and C. So let me put all three of them at low or 0. All right, so there we go. So let's run the circuit. All right, good. So now with all three inputs at 0, you realize that the indicator here is off. So it means that the first output is correct. All right, so remember what we're doing is to verify that this circuit matches what we have here in the truth table. All right, so for the second row, so A is low, B is low, and C is high. So we're supposed to get a low output. So it means that the indicator should be off. All right, so there we go. The indicator is off. Good. So let's go again. A remain low, B is high, and C is low. Indicator should be off. So there we go. Indicator is off. All right. Let's go again. A is low, B is high, C is high. Now the indicator should be on. So it means that the output is high. All right, good. So there we go. All right, let's continue again. So A is high, B is low, C is low, and the indicator here should be off. All right, so far we're going good. All right, so let's go again. So A, high, B, low, and C, high. Indicator should be off. All right, so there we go. So the indicator is off because the output is low. All right, good. So let's go again. So A, I, B, I, C, low. All right, so the indicator should be on because the output is I. So there we go. All right, good. So now to the final one. So A, I, B, I, and C, I. So the lamp or the indicator should remain on. All right, so there we go. So based on what we just did, this tells me that this circuit is the correct circuit. So let's move on to part 3. So it says, what is the minimum number of logic gates that may be used to design the operation stated in C? All right, so based on the number of logic gates that we have here, and based on what was stated in part C, that minimum value or minimum number of logic gates would be 3. All right, so for part 4, it says state the mathematical expression for output Y of this logic circuit. All right, good. So for this circuit, the mathematical expression, so we'd have to multiply AB and BC and then add both of them to get the output Y here. So this is it right here. So A times B plus B times C will give us Y. All right, so let's look at it on the circuit. Now to get the output here for this on the gate, we'd have to multiply A and B. So it means that at this point here, you would have A times B. All right, let me write that there. So at this point, you'd have A times B. So this is what you'd have to do to get the output for this AND gate. For the second AND gate here, again, you'd have to multiply B and C to get the output here. So it means that the operation would be B, that C. Now remember the mathematical operation for our gate is addition. So it means that in order to get an output here, you'd have to multiply A times B plus B times C. So it means that Y would equal to A dot B plus B dot C. All right. And that's the mathematical expression for the output. And that's how it is done. All right. So that's it for this question.